Hello everyone, nice to see you again. Okay, let me make sure I got everything to go. Ah, I flipped my computer too early. Where is my screen? Great! Well, I think that means that we're down to the last 2 weeks or something. First of all, that means that there's an exam on Friday. So there will be a test and it will talk about whatever we talk about up until the end of next time, which is Wednesday. And then there will be one more week after that where we talk about some other interesting topics in graph theory. And then I guess it goes into finals week. So congratulations, we're almost at the end of the semester. Hopefully the subject has been somewhat interesting so far. Now let's go and dig in some more into this Ramsey theory, which is what we talked about last time. So for the Ramsey theory, we showed something interesting last time, which I'm going to repeat. I'm going to repeat the statement that we wrote last time. Let's first remember the definitions. The Ramsey number, R, S, T, was the smallest number of vertices that you need in order to guarantee that when you color edges, something nice happens. So this was the minimum number of vertices such that every two coloring of the edges, two coloring means using at most two colors, using up to two colors. My words look huge. So first of all, it makes it easier for you guys to read, but unfortunately it makes it so that I can't draw as much. And I just realized it's because whenever I reboot the system that I use to do the drawing, it sort of changes the size. Oh no, what did I just do? I changed something which I didn't mean to change. Let's go and do that again. Come on. Here we go. I just need to readjust this. You're not seeing anything change because I'm doing it in my preview right now. And then I'm going to flip it back. Perfect. Here we go. Okay, so now we're back to normal size. And that way I can fit things onto a screen again. Right, so we want to know the minimum number of vertices so that whenever you take any two coloring of the edges has a I need to have two colors now. So there's a S and a T. So I'll say it has a red, KS, or a blue, KT. And that's a T, not a Z. I just have bad handwriting. So anyway, this is saying that the minimum number of vertices. And last time we showed something. We proved a theorem. Actually, this theorem is often called the Erdős-Szekérys bound. Erdős-Szekérys. This is an S. Erdős-Szekérys bound. And this Erdős-Szekérys, you may notice there was something else in this class that also had Erdős-Szekérys as a name. That was something about if I have any sequence of n numbers, n distinct numbers, then there's always a monotone subsequence of length at least square root n. We saw those two names there too. And it might seem interesting that they have similar flavor, these two results. This result is now when you have enough vertices, then there's always going to be a monochromatic something. And this Erdős-Szekérys result showed it was an inequality. Rs, T is at most Rs, T, maybe I was writing S minus 1, T, plus Rs, T minus 1. And what we showed last time, that just means that if you take this many vertices on the right, just translating this back into English, i.e. with this many vertices, you can guarantee a red KS or a blue KT. That's what we had last time. Now, we wanted to turn this into a bound. And something which I showed really quickly towards the end of the last time was like, hey, you can use this with induction to get a nice bound. So what we did last time is that somehow corollary, what we get from this is also in the corollary, we also using R1T is equal to 1 and Rs1 is equal to 1. We did that. We used those two last time. And let's now draw a little chart. If I have an S and a T, and we were writing inside this table upper bounds R st less than or equal to this, like the stuff that I write inside, then I can just write down some table. 1, 2, 3, 4, 1, 2, 3, 4, and so on. Okay, and I can put down some numbers. So all of these on the first row and the first column are ones. This is all stuff that I zoomed through last time, which is why I'm writing it down again this time. And I also just realized, for some reason, I don't hear anyone saying anything. But that might just be because no one said anything. Okay. so no, it's just, there's this like odd thing and little, I just wanted to make sure my settings were such that if anyone is saying something else, I'd hear. Okay, but let's continue. So what we did last time is we said, okay, for everything, you can write in that spot the sum of the numbers directly above and directly to the left. That's what this Erdős-Szekerish result gives you. So then I could write 2, 1 plus 2 is 3, 3 plus 1 is 4, 1 plus 2 is 3, 1 plus 3 is 4, 3 plus 3 is 6, and this is 6 plus 4 is 10, this is a 10, and this is a 20. And you see Pascal's triangle evolving. That's what we saw last time. This is exactly Pascal's triangle. Although it should probably be called Pascal's square at this point, if I draw it this way. Because it's just like you're filling it out as Pascal's triangle on the side. And this then immediately tells you, by this induction, RST is less than or equal to something, choose something. And you can already see it would be something, choose something because of the fact that I have all the things in the something, choose something form. And again, the way I usually figure this out is I'm like, okay, what are they? Well, you know, what's 10? 10 was 5, choose 2, right? So this 10 here, this 10 is 5, choose 2. So you're like, well, if that thing is 5, choose 2, and this 10 is also 5, choose 2, well, what are you choosing what? Effectively, because you see that the rows of Pascal's triangle are like these diagonals, the diagonal has constant s plus t value. I'm trying to motivate how the formula comes out. Because you see, you should tilt your head this way. This way. If you tilt your head this way, then somehow, based on the value of s plus t, that's telling you what row you are on Pascal's triangle. And so if s is 4 and t is 3, your row is 5. So it should be 4 plus 3 and then minus 2. It's s plus t minus 2. I'm just showing you how you would get, how you'd figure it out from here. That's 2, s plus t minus 2, sorry. And then what you're choosing, we could just say you're choosing s minus 1 or choosing t minus 1. I'll use s minus 1 because s comes before t in English. But I'm just showing, like, that's how you'd figure out what this particular choose is. And the way you know that s plus t should be on the top is because the top number is telling you like which of these slanted diagonals you're on. And as s plus t gets bigger, you go further and further down these slanted diagonals. And at the very, very beginning, like at this edge over here, that's a choose 0. And that's where s equals 1. So s minus 1 is 0 there. Are people good with this? Like this is now proving an upper bound on Ramsey numbers, which is really nice. Okay, well, let's think of what this actually means. We were curious about what was R33, right? Let's see, what does this tell you? So if I wanted to know what's R33, well, that's equal to 3 plus 3 is 6, minus 2 is 4. 3 minus 1 is 2. Oh, look at that. It works. So R33, we got the 6. And I mean, this is only showing you one direction, right? We had to show R33 equals 6 before. To show equals 6, we also had to say, look, you can make this 5 vertex colored edges thing, and that one has no monochromatic triangles. But to show that 6 is enough to guarantee, this is good. What about R44? R44 is at most 4 plus 4 is 8, minus 2 is 6. 4 minus 1 is 3. Is that right? Yeah. 6 choose 3. That's 6 times 5 times 4 over 3 factorial. Now 3 factorial happens to equal 6, so that cancels out. 5 times 4 is 20. Now, we know from Wikipedia that the R44 is not 20. It's actually less than 20. But that's okay. This is just telling you it's less than or equal to 20. 20 is enough. This was the story I told you about the 20 school children and noticing that there was always a monochromatic for like people who are all friends or for people who are not friends. But now you're starting to wonder, like, how bad does this get, right? Like, the answer for R44 maybe it was 17 or something. Well, in general, what is RTT? If I plug in, oh, I said TT. If S and T are the same, what kind of bound do you get here? R, T, and T is less than or equal to 2T minus 2, choose T minus 1. What's that like as T gets bigger and bigger? Any idea of, like, how biggish this is? What's the order of magnitude of something like this? I'm going to rewrite it on the next screen. So I'm going to write RTT less than or equal to 2T minus 2, choose T minus 1. RTT is less than or equal to 2T minus 2, choose T minus 1. What's the rate of growth here? Advait, what do you want to say? Exponential-ish maybe. What kind of answer is that? No, that's okay. Okay. It's a guess. Exponential-ish, maybe. How might we know? Does anyone want to give me an upper bound on this? It doesn't have to be exact. You can say like it's clearly at most something. Because we don't really like to write like choose stuff. Braden.
We could say 2t minus 2 to the t minus 1.
So it's definitely less than or equal to 2t. So I'm going to even do a little bit on that. 2t minus 2 to the t minus 1. Can I divide by t minus 1 factorial?
Yeah.
And what I just did here is like how I often do a choose. I go and multiply the big number times the number minus 1, times the number minus 1, times the number minus 1, and so on, as many times as I need to, which is the bottom number, and divide by the bottom number factorial. That is true. But that one, I can't understand either. Now it's very scary. There's this funny factorial there. If I want some dumb bound, like, Advait says exponential-ish maybe. I can't tell if this is exponential-ish maybe. Can anyone tell me something else? It can be like a pretty bad bound. I want another bound of the form. I'll write also. Because this is also, I'm just writing down a bunch of stuff that's true. 2t minus 2, choose t minus 1. Anyone else want to give me something else that it's at most? It could be like way off. Chris.
2t to the 2n.
2t, sorry?
2t to the 2n.
Okay, where's the n?
2n on top.
Yeah, but what is the n?
The n? Oh, I mean, I'm trying to sum it like across the row.
Okay, I want that. Yeah, okay. I see what you're doing. You want to sum across the row. I want that, okay? So if you're saying that you want to use the fact that Pascal's triangle has like 1, 1, 1, blah, 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 blah. And then at some point you've got this 1, 5, 10, 10, 5, 1. What do you mean by sum across the row? What did you want to say here?
So that is equal to 2n, so you have to do that, or 2 to the n.
Something like that. Okay, I know where you're going. Okay, so you're like, look at that. The fifth row of this thing, and all of these numbers are like 5 choose stuff, right? All of these things are 5 choose stuff. I'll write 5 choose x. And if you add up a bunch of stuff that is 5 choose stuff, then the sum is at most 2 to the number, 2 to that row. Let's use that. And that's exactly what I wanted. 2 to the power 2t minus 2. So 2 to the power n. Is that okay? That's true. Well, I just wanted to know, like, roughly what is this. So here, let's be even more rough. This is now definitely at most 2 to the 2t. Let's forget the minus 2. All right? And it's actually, I can rewrite that as 4 to the power t. So we just found out that this is at most exponential. It's not any bigger than exponential. But Advait says exponential-ish maybe, right? Like, what if we were just really bad with this bound? How far off could you be by saying, look at this, I got a giant row of binomial coefficients, and I'm just going to say that any one of them is less than the sum of the whole row. Well, it turns out that's not that bad. So it turns out that the central binomial coefficient, that's what this is called, the central binomial coefficient is not that far off from the whole sum. And this turns out to be a pretty good approximation. This is called a central binomial coefficient. Okay? And it actually turns out that, I'll write turns out that, if I take like n, choose n over 2, okay? And I'm just going to say n is the row that I'm on. Turns out that this is like approximately, a bunch of approximates. It's about 2 to the n, but divided by something. What should it be divided by? Well, it turns out that what it's divided by, if I want to write, I'm not done yet, okay? I'm going to rewrite this, and I'm going to write, and this is somehow related to, it's related to, this fact is related to the probability that if I flip n coins, I get exactly n over 2 heads. I mean, that's like exactly what this is related to, okay? The probability that if you flip n coins, get n over 2 heads. It's in my head anyway. But anyway, so this is heads. And the reason why it's related to this is because the probability that you get n over 2 heads out of n coin flips, isn't that like n choose n over 2, but divide by 2 to the n? You see that? Like this denominator here is like the reciprocal of that probability. Are people okay with that? Like there's this probability here. The probability here is called n choose n over 2 divided by 2 to the n. So this denominator here is just the reciprocal of that probability. Does anyone know what that might be? If you flip n coins, like 10,000 coins, if you flip 10,000 coins, what's the chance you get exactly 5,000 heads? Does anyone know the order of magnitude of this? This is related to statistics class. It has something to do with standard deviation, for goodness sakes. I'm curious, what's the order of magnitude? If I flip n coins, what's the chance that I have exactly half of them heads? Is it 1 over n? I mean, 1 over n would be like if getting any number of heads was equally likely. You see where I'm going with this? I'm like, it's actually 1 over n plus 1 would mean that everything is equally likely. Getting 0 heads, 1 head, 2 head, up to n heads. If the chance of getting exactly on the dot half of them, assume n is even by the way, getting half of them, that would be, if it was like all equal, it would be 1 over n plus 1. But what is it actually? Anyone took a statistics class who might know, like, there's this like funny curve thing. Advait.
I'm going to say, is this some sort of like central limit theorem type E something or the other?
So is it something like e something to the other? Well, the shape of the thing is e to the power minus x squared over 2, okay? Hey, while we're talking about this, I just want to show you how all of the math is related, okay? So we want to put something down there, and it actually turns out that if you do flip the coins, it does look something like this. By the way, if you ever are trying to draw this Gaussian curve, big tip, draw curve first and then axes. Because if you draw axes first, you'll never succeed in making the curve symmetric. But if you draw a curve first, like look at that, it's perfect. And not to mention the fact that you can even make it line up. So always draw curve first, then axes. But now if I've gotten this actually follows some kind of a Gaussian-ish thing with the E, right? This is like a some constant. This is a blob, some constant times e to the power minus like x squared over more stuff. Is this okay? I'm like, this should look somewhat familiar from a statistics class. Actually, there's like a 2 sigma squared. Maybe if you took the real class, you'll know that those things are there. And it looks something like this. And the mean is around n over 2. Okay, fine. It's not e to the minus x squared. I have to also do like, I think I need like x minus the mean squared. Hopefully this looks somewhat familiar. Like this is the Gaussian type thing. And this is saying approximately what it's becoming. Okay, it's related to this, but I want to know what's the probability that you nail right on the middle. And if you had a continuous probability, by the way, if I said what's the probability that if I choose a random number between 0 and 1, what's the probability it's exactly half? The answer to that question is unfortunately 0, because you won't hit it, right? But what's going on here is I have a discrete type thing. Yeah, Advait. Aha! So it's related to standard deviations. Yes, it's related to standard deviations. Yeah. So there's this standard deviation business, right? So now we've got these standard deviations. If I'm doing coin flips, by the way, what's going on here is like this is n over 2 plus, can I write sigma for a standard deviation? Again, I don't know the whole backgrounds of everyone who's taking this class. Some people may have taken a stats class, some people may not. But standard deviation is like, it looks to, I mean, as you flip more and more times, the curve ends up looking like this. And it goes between n over 2 plus sigma, n over 2 minus sigma. And you've said something about like, about a third of the probability lives here, about a third of the probability lives there. Okay. Does anyone know what's the standard deviation if you flip coins n times? If you flip a coin n times and I count how many heads I get, what order of magnitude is the standard deviation? Sean.
It's about root npq, so that's
Yeah.
root 1/4 n.
Okay, so there's this root npq, and again, this is not a stats class, so I'm not trying to prove everything. I'm just trying to help anyone who has taken a statistics anything, like connect dots in their heads about math. Okay, so there's this root npq, and that's like the standard deviation. So this is the sigma, is this root npq, and p is half, and q is half. Q is 1 minus p. So this is like root n-ish. The order of magnitude is root n-ish. What that root n-ish? So what that means is that the width here is about order of magnitude square root n. In that case, that's telling you that the chance that you get between n over 2 minus about square root n, maybe like 2 root n or something, to n over 2 plus like maybe 2 root n or something, the chance of being in that window is like 2/3. What can that tell you about the height of that thing? The question I'm asking is like, what's the height? Well, you know, like let's think about the way an integral is constructed, right? The way an integral is constructed is that this is a discrete distribution. So the n over 2 is like this bar here. It has a width. Is this okay? So I'm making like this histogram. I'm thinking even of the area underneath it. And the area underneath it, the area underneath like that particular piece whose width is 1. The width is 1. That width is 1. So I've got this width of 1, and that's nice. And this area underneath it is, you know, right here. But the important thing is, like, how wide is the whole thing anyway? The whole thing here, the whole width, is like order of magnitude square root of n. So if I wanted to know the whole width, it's like square root of n going from there to there. Why am I doing this? I'm trying to visually give you an idea of how tall this has to be. Because what I've just found out is I've gotten this like zoomed in spot here, okay? And I'm going to, I guess I'll draw a zoomed in spot right here, where zoomed in just means made it cleaner to just focus on some part. I have this part, okay? This is what I'm focusing on. I'm really curious how tall this thing is right here. What I want to know is the height. Okay, I want to know the height. That's an h, not an n. I want to know the height. And somehow I know the width has order of magnitude root n. So I'm going to write root n. I'm dropping the constants, but it's going to be of order of magnitude root n. And I also know something about the fraction of the area, which is that underneath this whole thing, under the whole thing, that corresponds to about 2/3 of the area is here. Area is about 2/3. Actually, I said area equals about 2/3 because that's how probability works. If you want to know the probability that you land between here and there, it's actually the integral. It's the amount of area underneath this curve. Can anyone use all this information that I've just drawn here to try to figure out what h might be? Braden.
H is going to be roughly 2/3 times root n. We're going to have that area. If we just imagine like as a rectangle.
Yes.
Base cuts width equals volume.
Yes. So what we're doing here is we're doing a lot of approximations where we're like, well, we might be off by a factor, like a constant factor. But the important thing here is inside our little bottom of this bell curve, between like that height and that height, that's only a constant factor of a difference. I actually don't know what it really is. You have to draw a bell curve to see. But it's not like the height here. It's not like the height here compared to the height there is multiplied by 10,000. It's like multiplied by at most 3. I'm just making that up. But over here now, if you imagine that the area under this blob thing is 2/3, well then, if you imagine it was like a rectangle, then the base is root n, the height is this height. H times root n has to have the same order of magnitude as 2/3. That's how you think of this, which is about the same order of magnitude as h times the square root of n. I'm just showing how these things actually make sense. I want to be like, I don't want to just be like, I pulled something out of a hat and well, there's a square root n all of a sudden. Instead, I want to say it actually follows from these notions of statistics, that if you just flip a coin enough times, the standard deviation of the number of heads is square root n order of magnitude. And so we can use that to go and look at this and say, well, the height of this thing, this column in the middle, that's going to be about 1 over root n multiplied by some constant. And the reason I drew this out to a width of 1 is another way of seeing that is that I have like about root n strips like that, and altogether they accumulate a total of 2/3. So all of this implies that the height is of the order of magnitude 1 over root n. Suddenly that means that this approximation that Chris gave is not that bad. Actually, Chris's thing, he told us 2 to the power 2t minus 2. But in reality, not only is it bigger equal, we also get the other way. This is less, it's not only is it the choose less than or equal to something, the choose is also bigger than or equal 2 to the 2t minus 2 over like some constant. I don't know what the constant is. It might even have a root and a pi inside it, but times the square root of 2t minus 2. Now, this is a blob, some like constant. Oops. This is a blob, some constant. Okay, now here's a question. If your bound is already like 2 to the power 2t minus 2, how significant is the square root of 2t minus 2? If someone told, yeah, it's not. Like if someone told you, hey, you know, my number, it's like at most 2 to the power, let's pretend t is 100. It's at most 2 to the power 198. But I might be off by a factor of the square root of 200. You're like, the square root of 200, what is that? That's like 14. You're off by a factor of at most 14. But the bound you just gave me was 2 to the power 198. Who cares about the 14? That is spare change. Does that make sense? So what I'm trying to emphasize is that the order of magnitude of the bound that we have just gotten is 4 to the power of t. Yeah, with some correction factor with like square root t-ish stuff. But that's already considered exponential. If you have an exponential thing and you divide it by a square root, it's still exponentially big. In fact, it's bigger than 3.9999 to the power t once your t is big enough. Okay, so all of this has gone to show that, so I'm going to write r t comma t is this less than 4 to the power t. And this argument that we have shown can't ever give you a better base of the exponent than 4. And this argument can't be improved to show r t comma t is less than 3.9999 to the t for all sufficiently large t. That was supposed to say large. Let me write it again more neatly. Large t. Notice I have this word sufficiently large. It's because weird stuff happens whenever you're doing like very small values. So the interesting thing we always want to know is when you have like really big values of t, what happens? So okay, we got a 4 to the t, and the question is, could we do better than that? Could we get like a 3.999 to the t? If anyone can prove this, by the way, for all sufficiently large t, you automatically get an A in the course. Actually, this is a very famous central hard problem of can anyone improve that bound? Nobody knows how to improve that bound to a different base of the exponent. And this is a deep question. It's like, such a nicely described problem. How can you not get a better thing than this? Actually, it was the equivalent of Reddit back then, but like on April 1st, a long, long time ago, on a website that was the equivalent of Reddit, it was called /dot. Someone posted something saying, here's a proof that RTT is less than this 3.9999 to the power t, because that would be cool. But it was April 1st, so it wasn't true. Okay, well now let's work from the other side. Oh, Eric, what do you want to ask?
Like, how big do you want that? Oh, we don't know RTT for 6, right? So
We don't even know it for 5. Yeah, but also, you see, the problem is I want to know this for sufficiently large, which means that if you wanted to prove this, even values of t equals 5, 6 wouldn't help you.
I'm just asking, like, for how much do we know it's like true?
Oh, yeah. Okay, so now let's try to see, like, how much do we know that it should even be this big, all right? So now let's start working from the other side. You have just gotten to the next part of the class. So the next part of the class is, well, let's try to prove the other way. Oh, yeah, before I do that, let me write in English what this means. I always need that when I'm learning something. I.e., if you have 4 to the t vertices and color all the edges with 2 colors, there's always a monochromatic KT. And that sets us up for the next thing, which is like, well, I mean, could it just be that we came up with a really lazy and lousy proof, right? Like if I was just proving something and I just, I prove it, this is enough. But maybe if you're a smarter person, you could find a more efficient way to be like, well, you're just wasting all of those vertices. I mean, look at how the proof worked. All we did is we said, pick any vertex, stick them off to the side, and think about how that vertex is adjacent to other vertices. Maybe that's just a dumb idea. Maybe you should use the whole graph at once, the whole coloring at once. Well, let's work on the other direction. Now, think about the other side. The other side means, hey, what if we can just come up with some ways of coloring edges which avoid monochromatic KTs, but I want a lot of vertices. Find a nifty way to color all the edges with no monochromatic KTs. Right? Like, let's just try to do that. And the easiest way to do this is, hey, you know what? If I have t minus 1 vertices, I can do this for you. Because there's no monochromatic KT, there's not even a t. Right? So like the easiest thing is to do easy, let's just call it easiest, with t minus 1 vertices, just do anything. Okay, that's one. But now when you're working from this other side, we want to do it with as many vertices as possible. But want to do this with as many vertices as possible. And of course, the where we're trying to go to is there's 4 to the t over there, right? One of the bounds says, hey, if you got me 4 to the t vertices, then no matter how hard you try to color these edges, you're gonna have a monochromatic KT. Okay, over here we can do it with t minus 1 to avoid. Can anyone come up with something a bit more sophisticated than t minus 1? I claim there's a way to do it with t minus 1 whole thing squared. That was a hint. Also, not bad can do with t minus 1 squared vertices. That was a hint. Can anyone think of a way to do this? You just have to, all you have to do is say like, look, put the vertices like so, color like this, and we'll just see that there's no monochromatic KT. Braden.
You can split them into t minus 1 groups of t minus 1.
Ah.
Within the groups, you color in blue. Across the groups, you color in red.
Okay, so we have t minus 1 groups. And within the groups, we color them blue. So I'm just going to kind of do this blue shading inside, right? So each group inside is blue. Let's just draw an arrow. Inside each, all blue edges. Remember, we're coloring edges, not vertices. And then between them, it's like red stuff. Oh, let me just do one. Between them, it's like red stuff. Did that sort of make sense? It's just like every edge is either inside a group or crossing between groups. That's for sure. T minus 1 is not supposed to just be 3, but in general, you just have a bunch of these groups. Okay. And here, between groups, red. Now, why is it that there's no blue KT? Well, there's just no blue KT. There's no room. There's no room. The biggest blue thing is T minus 1. The slightly non-obvious one is, why is there no red KT? Anyone else want to help me with that? I just want to make sure everyone's on the same page. Why is there no red KT in this thing? Nancy.
You have to get represent each group and then T minus one groups.
Your key observation was that if you try to make a red thing, you are not allowed to pick 2 from a group, or else you immediately got a blue edge. If you want to make an all red, your maximum is 1 per group. Did that make sense to people? Because if you're trying to make a red thing and you got 2 in a group, inside the group, those are all blue. So you just got yourself a blue edge. That's bad. So let me just emphasize that. So I don't have space to write it down, but I'll just say that's why your biggest red thing is 1 per group. And that's why there are T minus 1 groups. So you just can't get a red KT. And so this is the construction. You can just look at it, you can analyze it like that, and you can say, yep, I can do it with T minus 1 squared. And what you're looking at here was the state of the art for like a decade. Nobody was able to find a better construction. Now that's kind of hard. Like that's kind of like a crazy, crazy gap, right? It's like on the one hand, you can show that if you just had 4 to the T vertices, then we're good. Then no matter what, there's going to be this monochromatic thing. But how can it be that despite trying as hard as we can, the best thing we could possibly construct only has T minus 1 squared vertices? That's like not even exponential at all. That's barely like polynomial-ish, right? Like it's just T squared. And it's an amazing fact that Paul Erdős came up with a very nifty way to go and construct a way or prove that there's a way to make this kind of a coloring, which people couldn't come up with. And the key is actually related to probability. Now, to maybe give some idea of why it could be, like how could it be that, probability is the way to solve this thing? Well, first of all, let me go and do the analysis. And then afterwards, we'll go back and talk about some very interesting paradox that has uncovered. So the first thing is like, it does turn out that the exponential is the right answer. It is going to be some exponential. However, it's not going to be, we're not going to get a bound of 4 to the power t. We'll get a bound of around square root 2 to the power t. So here's a remarkable construction, or construction is the wrong word, but a remarkable way of showing that there's a way to color. Okay? So what we'll do here is, let's use even t's. I don't care too much about the odd evenness, because once your number gets big enough, then asymptotically, it's about the same. Okay? So what we'll do is we'll show, this is by Erdős. For every positive even t, okay, it turns out that there's a way to color. There's a way to color all of the edges on, let's write 2 to the power of t over 2 vertices with no monochromatic KTs. Now this is cool. This tells you square root 2 to the power t. This is square root 2 to the power t. This tells you that square root 2 to the power t is a lower bound. And so then the answer is somewhere between square root 2 to the power t and 4 to the power t. That's exponential. And one of the deepest questions in math is to somehow find a way to either improve this base of the exponent, square root 2, or improve the other base of the exponent, 4, and try to squeeze them down. But for over half a century, nobody has managed to move those bases of the exponents. Really neat question. All right. Now, the interesting thing here is I kept telling you about the word construction, and I immediately took back my sentence and said, oh no, he showed there's a way to do it. It doesn't mean that he has a way that he can show you. And the reason is because the proof of this is to hire monkeys. Lots and lots and lots of monkeys, like exponentially many monkeys, which is obviously not possible. But we're going to do something completely random. The way this proof works is you just go and say, look, let's just color every edge randomly. Again, I don't know if monkeys are really that random. Maybe that was a bad example. But some people talk about monkeys typing Shakespeare if they just punch the typewriter enough times. But the idea here is that just put down this many vertices, 2 to the t minus 2 to the power t over 2 vertices. And then for every possible edge, flip a coin to decide if it should be red or blue independently. Aha. So now we're getting to something inside the homework, I guess. Okay, cool. So we hire monkeys. And what we do is you put down 2 to the power t over 2 vertices. Oh, let's call that n, by the way. It's going to be very useful for me to call that n. So I'm going to clean up back to here. I'm going to say put down n, which is equal to 2 to the power t over 2 vertices. I'm only writing it n because I want to talk about n sometimes, and then, soon we'll turn everything into t's. Put down this many vertices, and for each of the, I guess I'll write n now, each of the n choose 2 edges, edges, this many edges, you randomly color red or blue with 50-50 chance independently. Independently color red or blue equiprobably. That just means 50-50 chance. Okay, so what we just did is we hired a team of monkeys. And the claim is that this works out. Okay, let's see. First of all, what do you mean just this works out? I mean, maybe the monkeys decide that they all are red. I should say, show that this works out means we will prove that there's a decent chance that somehow there's no monochromatic KT in the end. Will prove there's a decent chance that there's no monochromatic KT in the end. Well, when they're done. When done. Now, notice I said there's a decent chance because there's like a indecent chance, but a positive chance that the monkeys just all decided to color red. By the way, that's extraordinarily unlikely because each of them is independently deciding, right? So in this like really crazy tiny chance of the probability space, it's like, oh, they're all red. Well, then that's not true. I mean, then there's clearly a monochromatic KT because in fact, the whole thing is monochromatic. But the claim is that's like highly, highly unlikely. So we are now going to try to prove that with decent chance, there's no monochromatic KT. How does this work? The way you do this is we'll bound the probability of failing. So by showing that the probability, I'll write PR for probability that some T vertex subset is monochromatic is like less than 1. I should probably have been careful about this word decent. Here with this decent, I'm actually just showing that it's a non-zero chance. There's like some possibility that the monkeys succeed. Okay, and maybe that's what you should guess because if you just hired monkeys, what's the chance they'll succeed? I just want to show there's some hope in the world that they succeed. And by the way, if I did this, that will prove the statement, right? If I can show that if I hire monkeys, there's some chance, positive chance that the monkeys succeed, Well, then there's a way to do it. That's called the probabilistic method. It's really cool. It's like if I just show there's some probability of success, positive probability of success, then it exists. Okay, that was Paul Erdős's idea. Now, how do you do this? Maybe let me put in quotes. That's called the probabilistic method. Okay? Now, how do you do this? Well, if I want to do this, one way is just to say, well, what if I just look at my n vertices and I assign monkey supervisors to stare at sets of t vertices? So the next thing you do is you hire lots of monkey supervisors and choose t supervisors, each to watch a subset S, well, I'll give it a name in a moment, a subset of t vertices. So what's going to happen is that I have these monkeys randomly coloring, and I also have a whole bunch of supervisors. The supervisors, each supervisor is responsible for a different set of t vertices. And I just need to show that the probability that some supervisor sees that the monkeys screwed up on their set, I need to show that probability is less than 1. Suffices to show that the probability that some supervisor sees monochromatic is less than 1. Are people okay with this? Actually, I shouldn't even write the word suffices to show. I'll write equivalent to show, because that's exactly what we've done. Are people okay with my equivalence? Because up there we said, as soon as you found, we want to show that there's no t-vertex subset where all the edges are monochromatic. That's equivalent to making sure that I just assign my supervisors to go and watch. Oh, don't you want to show it's greater than 0? Do I? Well, let's see. Uh-oh. Now we got lots of questions here. Some probability. Okay. Sorry about that. How do you show some probability? Do you need the expected value to be bigger than 1? No, actually, I don't need to worry about expected value here, because I'm just trying to say that there's some probability. But Andrew, you're saying something about greater than 0. Do you want to say again what you're thinking?
I was just thinking that, like, showing that the probability is less than 1 doesn't mean the probability is 0. So I'm confused on how this helps us.
Thank you. So the important thing is this is the complement of what I want. I want to show there's a decent chance that there's no monochromatic. So if I flip the truth of that logically, the opposite of no monochromatic is some monochromatic.
Okay, that makes sense. Thank you.
Thank you so much for asking, because that shows that I jumped too fast. So over here, I want to show that there's no monochromatic, but it's hard to estimate that probability of no something. So I flip it around and I say, let's show that the probability of the opposite, which is that there is something, is less than 1. And these two probabilities are complementary. They add up to 1. Advait.
I have an idea.
You have an idea. Okay, so first of all, we're all down to here now. We just need to know what's the probability that some supervisor sees mono. What's your idea?
It's about that. So sum is also too hard. What if we just figure out the probability that some given supervisor sees a monochromatic, and then just stupid bound it by adding up over all supervisors?
Okay, so what you're saying is that, look, don't all the supervisors have the same probability of seeing mono? Like, that's actually true. If you just go and say, hey, you're in charge of those t vertices, what's the chance that that's mono? That's going to be exactly the same as somebody else's job. So what you're about to use is you're about to use the very important probability inequality, A union B union C, and like a bunch of them, union Z. I guess I have 26 things. But anyway, this is less than or equal to the probability of them added up. Probability of A, probability of B, all the way to probability of Z. This is called the union bound. Is that okay? Like that's called like, that's the inclusion principle. The inclusion-exclusion principle is you add and subtract and add and subtract. The inclusion principle is called like, hey, look at this. I got this nice Venn diagram. I'm just going to add up the probabilities and call it a day. Well, that's an upper bound because of all your stupid overlaps, right? So that's why Advait says this is the stupid way. Just like add up the probabilities. So now let's see. What's each of them individually? Probability that the supervisor of vertices, let's give them numbers, 1, 2, up until t, sees mono. What is this exactly? We can write a formula. What is exactly the probability that the supervisor in charge of these particular t vertices, like these t vertices, sees that all the edges are the same color? That's equal to something. Advait, you had the idea.
Is it 1 over 2 to the t minus 1?
Close. Close.
Sorry, not these two. 1 over 2 to the power of, these 2 minus 1.
Okay, I'm going to do it in two parts.
Yeah, there we go.
Okay? So what we just did here is we said, look, each of those edges has to be the same color. Oh, well, we can say they're either all red or all blue, right? So the all red, that's 1/2 to the power t choose 2. The all blue is the same. That's why there's a 2 times. Is that okay with people? It's like if I just declared my one color all red, that's half times half times half times half. There's t choose 2 edges to worry about. And then I do the same thing with blue. Blue, 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 half, 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 half. When you add the 2 together, it just doubles one of them. Okay. Now let's put them together because I just want to show you the punchline. I know we're over time, but let's show the punchline here. So what's the probability that some supervisor sees mono? Probability that some supervisor sees mono, then that's less than or equal to the number of supervisors times this probability we just got, 2 and 1 over 2 to the power t choose 2. How many supervisors are there? There were n vertices. Braden. We're going to fill those in a second. That's good. So n choose t, and write the same thing I had before, times 2 to the power t choose 2. And now remember what n is. But before remembering what n is, I actually want to use another inequality. I don't like these chooses. I'm going to use something that came up earlier today. N choose t is at most n to the power t over t factorial. And then times 2 times 1 over 2 to the power t choose 2. We already saw this earlier today. N choose t is at most n times n minus 1 times n minus 2. Do it t times and then divide by t factorial. Now let's put in what Braden said, which is what is n anyway? N is 2 to the power t. So this is 2 to the t squared over 2 over t factorial times 2 times. Now I'm going to go and simplify 2 to the t choose 2 also. T choose 2, by the way, is t squared over 2 minus t over 2. What I just did is I just did t choose 2 is equal to t times t minus 1 over 2, which is t squared minus t over 2. These are all t's, not z's. Why did I do this? Something cool just happened. Advait. Bam! That's gone. 2 to the power t squared over 2. There's a t squared over 2. Let's clean it up. What is this? This is equal to, there's a 2 in front. The 2 to the minus t over 2 goes up top. 2 to the t over 2, not a z, it's a t, over t factorial. Do I have reason to expect that this is less than 1? That was my goal. I wanted this to be less than 1. Why are we happy? The reason we're happy is because the t factorial is insane. Like on top I have an exponential, and on the bottom I have a factorial. Actually, when you have a factorial, you get to multiply by bigger numbers every time. What's 100 factorial? Well, it's 1 times 2 times 3 times 4 times 5. It just gets bigger and bigger. And on top, if t was 100, it's like 2 times root 2 times root 2 times root 2 times root 2. It doesn't get any bigger. Does this make sense? So something really exciting about this is actually it turns out, even if t is 2, I think this is true. If t is 2, Or is it not true? Oh, no. Well, if t is 2, it's not interesting. So, I mean, not interesting meaning that's like Ramsey number 2, 2. But if t is 4, already for t equals 4, I will get 2 times 2 squared, which is 8, divided by 4 factorial, which is less than 1. So I'll write that this thing is less than 1 for all, we were doing even t's, right? All t's at least 4. Bam! So the monkeys work. But the interesting thing about these monkeys is, first of all, we've just shown that actually for all the t's which are, reasonable, which is bigger than 4, bigger equal 4, the monkeys have some chance in the world of succeeding. But there's something else even more surprising. Suppose t is 100. Like, what is this about? If t is 100 and you plug 100 in, what is that right-hand side very close to? 0. 0. Actually, your monkeys are probably going to succeed. Like, almost definitely going to succeed. Like, really cool fact is this actually goes to 0 for big T. That's actually really surprising. It's like for over a decade, nobody could find an interesting way to color the edges. They just couldn't find them. But somehow if you just hire monkeys, it just works. And now the interesting thing is, to this date, nobody knows a great way of doing this other than randomly hiring monkeys. A great way of like being able to get this exponential bound. And the thing I'll leave you with is like, how could you expect something like this ever to be the case? Like, so there's a true fact, but somehow the only way you can get to it is through monkeys. And this is the thought I leave people with. Hey, can someone give me a random number between 0 and 1? Just like type it into the chat or something. Random number between 0 and 1. Thank you guys. All these numbers. They're all rational, guys. They're all rational. What's the probability that if I ask you, give me a number between 0 and 1 and it comes back rational? What's the probability of that? Actually, that's 0. Okay, now people are being kind of clever. But I'm saying like the chance is 0. So what we just witnessed is like a probability 0 event out of this room of like all these humans. How in the world are we so good at coming up with probability 0 things? Or should I flip it and say, how in the world are we so lousy at coming up with probability 1 things? Because even the pi over 4, what I'll tell you there is you can do more fancy stuff and you can explain and you can prove that the number of different strings of finite length of characters from the keyboard is also countable. So in fact, anything that you could possibly type to me would be a probability 0 event. So I'm just sort of explaining that somehow it is kind of interesting. There's these things which we are very good at making, which are like probability 0, and there's some things that we can't touch very well, which are probability 1. I think I would leave it with that. So we'll continue next time with a different topic.
Thank you.